Hello friends, welcome back to my YouTube channel. Today I will continue my discussion on the Ponchon-Savarit method. So this will be 39th part of my discussion on distillation. And as far as the Ponchon-Savarit method is concerned, today I will be discussing one numerical where we will learn how to use the Ponchon-Savarit method to find the number of equilibrium stages or number of theoretical stages or number of ideal stages in a typical tray column. We will also learn how to find out the minimum number of stages in a tray column when it operates under total reflux. Earlier in my previous videos, I have discussed how to use the McCabe-Thiele method to get those minimum number of stages. Today, we will learn how we can use the Ponchon-Savarit method to get the minimum number of stages. Along with this, we will also learn to find the minimum reflux ratio by using the Ponchon-Savarit method. So this being first numerical on that is based on the Ponchon-Savarit method. That's why I'm calling it as numerical number 1. I'm calling it as numerical number 1. To begin with, we will know, first we will look at the numerical statement. The statement goes like this. The feed to a fractionating column is a binary liquid solution of heptane and ethyl benzene, and it is admitted at a rate of 5000 kg per hour. The feed enters the column as a saturated solution and contains 45 mole % of heptane. The column operates at a total pressure of 1 atmosphere and produces distillate that contains 98 mole % of heptane. The bottom product obtained contains 98 mole % of ethyl benzene. The other part of the numerical, based on this data or based on the data that is given, we are supposed to find out the molar flow rates of the distillate and bottom product, molar latent heats of vaporization of the two components, the minimum reflux ratio or the number of theoretical stages for an operating reflux ratio of 2.5, the minimum number of theoretical stages at the total reflux, and the last question is the heat load on the condenser and the reboiler, which is to be calculated in kilocalories per hour. So these are the questions, or these are the quantities that are supposed to be found out. Molar flow rates of the products, that is top product, the distillate and the bottom product. Then point number 2 is something different, because purposely I am going to discuss this because this will tell you how to use the enthalpy concentration diagram for a mixture to get the molar latent heats of vaporization of the components that are present in the mixture. So you'll come to know how to use the enthalpy concentration diagram. Then we are supposed to find out the minimum reflux ratio, then the number of theoretical stages when the operating reflux ratio is 2.5. Then we also are supposed to find the minimum number of theoretical stages at the total reflux. And finally, we also have to find the heat load on the condenser and the reboiler. That is, we are supposed to find out condenser and reboiler duties that we are supposed to report in kilocalories per hour. So these are the quantities that are to be calculated. Then the enthalpy concentration data is provided to us. So you can see the data is provided in this table. So you have X, which is mole fraction of the more volatile component in the liquid phase, various values of X. Then you have Y, that is mole fraction of the more volatile component in the vapor phase. Then you have HEL, which is enthalpies of saturated liquid solution. This is given in kilocalories per kilomole. Then you have Hg, various values of Hg. So these are enthalpies of saturated vapor mixture, and that is also given in kilocalories per kilomole. So enthalpy concentration data is provided to us, and we are going to use that to plot the enthalpy concentration diagram. So we'll come to know about it shortly. So first, let us collect the data that is given to us. What components are involved? There are two components. One is heptane and the other one is ethyl benzene. Now we need to decide which one is the more volatile component. So for that, we are going to use one information that is given to us. So how to decide the more volatile component? We know the major component in distillate is heptane, because as per the information that is given in the numerical, the distillate is containing 98% of the distillate is heptane. And since heptane is the major component in the distillate, you can directly conclude, or you can easily conclude, that heptane is the more volatile component. What is the basis for this conclusion? The basis is major component in the distillate is heptane. Of course, if you know the boiling points, you can easily decide. If heptane is the more volatile component, it is going to have a lower boiling point. But if you don't know the boiling points and you have this information, what is the information? Distillate is containing 98% mole of heptane in it. So that means you can conclude that heptane is the more volatile component. If they give you the boiling points, then you can easily decide. So if that information is not given to you, then you just look at the major component in the distillate. That will be the more volatile component. Then what information is given regarding the feed? So you have a solution of heptane and ethyl benzene. Heptane, let us denote it as A, and ethyl benzene as B, because usually we use the notation A to represent the more volatile component. This is our practice. It is up to you. So let me call heptane as A and ethyl benzene as B. It is a saturated solution. The feed solution is a saturated solution. That is, it is a liquid solution at its bubble point. What is the meaning of this? The meaning is the value of the parameter Q for feed is 1. Q is equal to 1. But we don't need value of Q in the Ponchon-Savarit method. But as a practice of noting down what is given and what are the implications of the given data, I have written this. Q is equal to 1. That means for a saturated solution, value of the parameter Q is 1. Then mass flow rate of the feed is given to us. So let me denote it by yum. So yum is 5,000 kg per hour. Mass flow rate is given to us. And in our calculations, we will have to convert it to kilomole per hour. So that we will be doing in our calculations. For time being, let us understand that the mass flow rate is, they have given the mass flow rate. It is 5,000 kg per hour. I am denoting that by yum. Then composition of the feed is also given. The feed is containing 45% mole of A, and the remaining amount, that is 55% mole, will be of B. That means in this case, XF is 0.45. You know XF is the mole fraction of the more volatile component in the feed solution, and in this case it is heptane. So since the composition is 45% mole, XF will be equal to 0.45. Then you also have some information about the distillate. What is that information? 98% mole of A is present in distillate and the remaining 2% mole is of B. So that means we know XD. XD is 0.98, 98%. So that would be 98 by 100. That will give us the mole fraction. That is XD, mole fraction of A, mole fraction of the more volatile component in the distillate. XD is 0.98. Then for the bottom product, the composition is, the bottom product is containing 98% mole of B and 2% mole of A. The major component in the bottom product is B, that is ethyl benzene. So that is less volatile component out of the two. Okay. So that means mole fraction of the more volatile component, which we denote by XW, is 0.02. So you have the information regarding the bottom product. Then the reflux ratio that is to be used to find the number of ideal stages that is given to us, it is 2.5. R is 2.5. So this is the information that is provided to us, and we are supposed to use this information to do all those calculations to find out the quantities that are given or that are supposed to be calculated based on all this given data. Then the enthalpy concentration data is also given because it is given in the table. So you have mole fraction of A in the liquid solution, mole Y, that is mole fraction of A in the vapor mixture, HL, that is molar enthalpies of saturated liquid solution, then molar enthalpies of saturated vapor mixture. Why molar? Because we are talking about enthalpy per unit mole, kilocalories per kilomole. Then what are we supposed to find out? We are supposed to find out the molar flow rates of distillate and the bottom product. Then we are supposed to find out molar latent heats of vaporization of the two components. That is, we will be calculating lambda A and lambda B. Rather than calculating, we will be finding, or we will be knowing, we will be noting down the values, and for that we will be using the NB concentration diagram. So lambda A and lambda B we will be reporting. Then the minimum reflux ratio we will be reporting, that is R minimum. Then we will be finding the number of theoretical stages for an operating reflux ratio of 2.5. So we will be reporting the number of ideal stages. Then the minimum number of theoretical stages which come into picture when the column operates at total reflux, that also we are going to find out. And finally, we are going to calculate the heat load on the condenser and the reboiler in kilocalories per hour. So we are going to find QC and we are going to find out QR. QC in this case is heat load on the condenser, or in other words, this is heat duty of the condenser, and QR is heat load on the reboiler. That is heat duty of the reboiler. Okay, so now we know what is the numerical statement, and then we have collected the information that is given to us. Now we will use that information to do all these calculations. So let us make it. So let us solve the numerical. First step is we need to convert the mass flow rate into molar flow rate, because flow rate of the feed is what they have given is the mass flow rate, kg per hour, and we have to convert it to kilomole per hour, that is F. So first step will be finding or converting the mass flow rate into the molar flow rate. For that, we need the average molecular weight of the feed. And how are you going to calculate the average molecular weight? Average molecular weight is equal to Ma into Xf plus Mb into 1 minus Xf. That is molecular weight of A into its mole fraction in the feed plus molecular weight of B into its mole fraction in the feed. Now, you may wonder why it is 1 minus Xf, because there are only two components. Let us say Xa, there are two components, A and B. So, sum of mole fractions of the two components is equal to 1. And mole fraction of A in the feed, we are denoting that by Xf. So, that means Xb, that is mole fraction of B in this case, will be 1 minus Xf. So, that's why you have 1 minus Xf in the equation. So, average molecular weight is M average is equal to molecular weight of A into mole fraction of A plus molecular weight of B into mole fraction of B. So, M average is equal to Ma into Xf plus Mb into 1 minus Xf. So, molecular weight of A, that is molecular weight of 15 is 100. You can check that. Then molecular weight of B is 106. Ethyl benzene. Molecular weight of ethyl benzene is 106. Xf is 0.45. So, all that we need to solve or to get M average, that is average molecular weight, you have that with us. So, let us use those values. So, this will give us M average is equal to 100 into 0.45 plus 106 into 1 minus 0.45, which gives us average molecular weight as 103.3. So, once you get the average molecular weight, you can find or you can convert the flow rate from mass flow rate to molar flow rate by dividing the mass flow rate with the average molecular weight. And why we are doing this? Because if you have mass in kg, let us say mass of a component, then how to convert these kgs into kilomoles? You have to divide with the molecular weight. But in our case, feed is a solution. It is not any pure component. That's why instead of using the molecular weight, simple molecular weight, we need to use the average molecular weight. And that's why we have first found out the average molecular weight. Okay, so therefore, the mass flow rate will be converted to molar flow rate in this way. F is equal to the mass flow rate divided by average molecular weight. Again, the same concept, that is number of moles is equal to mass upon molecular weight. Mass upon molecular weight. So, I am dividing the mass flow rate with molecular weight. But since this is a solution, I will have to use the average molecular weight. So, M is known to us, it is 5000 kg per hour, and we just have got the value of M average. So, let us use like given or known values to get the molar flow rate. So, F will be 5000 divided by 103.3, that is F is equal to 48.40 kilomole per hour. So, in this way, we have converted mass flow rate into the molar flow rate. So, feed is entering at this rate 48.40 kilomole per hour. Then the next step is after converting mass flow rate into molar flow rate. Next step is we will be calculating D and W. What is D? Molar flow rate of the distillate. And what is W? molar flow rate of the bottom product. And this is the first question that is given. So that is asked in the numerical. So let us calculate D and W. So for that we are going to use steady state total material balance, which is given as F is equal to D plus W. Now F is known to us. We just have got a 10 kilomole per hour. F is 48.40 kilomole per hour. We don't know what is D and we also don't know what is W. So I will simply write the equation as 48.40 is equal to D plus W, and then I am going to call it as equation number 1. Then I will be using steady state material balance for A, for the more volatile component. So how to write this? This will be written like this: F into XF, that is equal to D into XD plus W into XW. And what you know, F is known to you, 48.40, XF is known, 0.45, XD is known, it is 0.98, and XW is also known, it is 0.02. So if you use these values, it will be 48.40 into 0.45 is equal to D into 0.98 plus W into 0.02. So that is 21.78. 48.40 into 0.45 is 0.45 is 21.78. So 21.78 is equal to 0.98 D plus 0.02 W. And then I will write it in a different way. 0.98 D plus 0.02 W is equal to 21.78. And now I am calling this as equation number 2. So if you look at equation number 1 and equation number 2, you will come to know there are two unknown quantities that are present in these two equations. Which are these quantities? D and W. So you have two equations, you have two unknowns that are to be found out. So you can easily solve the two equations simultaneously and get the values of unknown quantities. So for that, what I will do, I will use equation. So from equation 1, I will write an equation for W. So from equation 1, W can be written as W is equal to 48.40 minus D. And I am going to use this equation for W in equation number 2. So that means over here, W will be replaced with 48.40 minus D. So if I do that, I will be getting 0.98 into D plus 0.02. Now W is being replaced with this equation. So 0.02 into 48.40 minus D, that is equal to 21.78. So if you simplify this, this will be 0.98 into D plus 0.968. 0.02 into 48.40 is 0.968 minus 0.02 into D, that is equal to 21.78. So 0.98 D minus 0.02 D is 0.96 D. And if I take 0.968 on the other side, this will be 21.78 minus 0.968. So therefore, 0.96 D is equal to 20.81. 21.78 minus 0.968 is 20.81. That is D is equal to 20.81 divided by 0.96. That is D is equal to 21.68 kilomole per hour. Once you get D, you can use the equation for W to get its value. So since W is 48.40 minus D and D we just got, so therefore W will be 48.40 minus 21.68. That is W comes out to be 26.72 kilomole per hour. So with this, we have got values of D and W. We have solved the first question. Molar flow rate of the distillate 21.68 kilomole per hour and molar flow rate of the bottom product 26.72 kilomole per hour. Then the next step after getting D and W, we will have to plot the enthalpy concentration diagram. And for this, they have provided the enthalpy concentration data and we will be using it. How to use it or how to plot the enthalpy concentration diagram, let us first understand. So for enthalpy concentration diagram, we are going to plot HL and HG, all these values on the y-axis. Enthalpies will be plotted on the y-axis, whereas mole fractions, that is X and Y, they will be plotted on the x-axis. And for this, enthalpies of the liquid solution will be plotted against the mole fraction of the more volatile component in the liquid solution, that is HL versus X. And enthalpies of the saturated vapor, they will be plotted against mole fraction of the more volatile component in the vapor phase, that is Y. So we are going to get the two curves, HL versus X and HG versus Y, when you plot the enthalpy concentration diagram. So now I will show you. So now you can see the graph. So enthalpies, we are going to plot on the y-axis, and mole fractions we are going to plot on the x-axis. And since delta W will be located on the negative, that is in the fourth quadrant, you can say. So that's why we need the negative part of the y-axis as well, and that's why I have shown that. So the range I have decided based on the values, enthalpy values that are given in the table. So that this range, or you can say the scale, covers that range. Accordingly, you can decide the scale. It will depend on what data is given to us. For this particular numerical, based on the data, this scale is suitable for me. And then you have x is equal to y is equal to 0 axis, that is x axis is over here, and on x axis 1 centimeter is taken to be 0.1. And you on x axis both x and y, they are plotted, and on the y axis enthalpies HL and HG are plotted. So if you plot, as I said, we are supposed to plot. Let me show over here. HL versus X and HG versus Y. So HL will be plotted against corresponding X values and HG will be plotted against corresponding Y values. So that will give us the two curves. Now those two curves are simultaneously being drawn on this graph. Let me tell you. The upper curve. What is this curve? This is HG versus Y curve, or you also call that as the dew point curve. The lower curve is a plot of HL versus X. We also call that as bubble point curve. Why bubble point curve? Because every point on this curve represents a bubble point. Similarly, every point on the upper curve represents a dew point. That's why the upper curve is the dew point curve and lower curve is the bubble point curve. So in this way, you have to plot the enthalpy concentration diagram, HL versus X and HG versus Y, to get this graph. Now from this graph, you can get the molar latent heats of vaporization of A and B. So let us learn how you can do that. So lambda A, that is molar latent heat of vaporization of A, will be the distance between the two curves at this end, x is equal to 1 and y is equal to 1 end. So this end is x is equal to 1, y is equal to 1. So this end, you must have, if you have seen my earlier video, I have explained why the end x is equal to 1 and y is equal to 1 represents pure A, whereas the other end, x is equal to 0 and y is equal to 0, it represents pure B. So I have explained that. You please watch that video. Now let us come back to our calculations. Lambda A, that is molar latent heat of vaporization of A. How you can get? That is nothing but this distance. That is nothing but this distance. So this is lambda A. This is lambda A. So this point, it is value of Hg, and that is at y is equal to 1. And this point is HL at x is equal to 1. So Hg minus HL, that is enthalpy of saturated vapor minus enthalpy of saturated liquid, is nothing but the molar latent heat of vaporization of that component. Which component in this case? It is E. In short, you need to find out this distance. You need to measure this distance, and that distance has to be measured in terms of the scale enthalpies. So to make the calculation simple, I have used this notation. Now I'll just erase everything because I hope you have understood the concept how we are going to get lambda E. So I have shown over here. So lambda A is Hg at y is equal to 1. So this is Hg at y is equal to 1 minus HL at x is equal to 1. This is HL at x is equal to 1. And these values are, even there is no need of measuring the distance, because these values, they are given in the data that is provided to us. So I can show that. So you have this data, and at x is equal to 1, y is equal to 1, the values are provided to us. HL at x is equal to 1 is 5100 and Hg at y is equal to 1 is 12675. So these two values are known to us. They are given. Or the other way is you just measure this distance. That will be lambda I. So here Hg at y is equal to 1 is 12675 kilocalorie per kilomole, and HL at x is equal to 1 is 5100 kilocalories per kilomole. So now the simple task is you just have to use these values to get lambda A. So lambda A will be equal to 12675 minus 5100. That gives us lambda A as 7575 kilocalories per kilomole, and that is nothing but the molar latent heat of vaporization of your A. What is A? 15. Let us find out lambda B. So lambda B will be obtained. Lambda B is this distance. Lambda B is this distance. That is enthalpy at this point minus enthalpy at this point. What is enthalpy at this point? Enthalpy at this point, it is Hg at y is equal to 0. And what is enthalpy at this point? HL at x is equal to 0. Again, you don't have to read those values from the graph, because those values are provided to us in the data. So I'll show you. So you have x is equal to 0, y is equal to 0. At x is equal to 0, HL is 5920, and at y is equal to 0, Hg is 14520 kilocalories per kilomole. So that is Hg at y is equal to 1 is 14520 kilocalories per kilomole, and HL at x is equal to 0 is 5920 kilocalories per kilomole. So you just have to use these values. Therefore, lambda B will be equal to 14520 minus 5920. That is lambda B is equal to 8600 kilocalories per kilomole. That is molar latent heat of vaporization of pure B, that is ethyl benzene, is 8600 kilocalories per kilomole. So in this way, we get an answer to the second question that was asked to us. We were asked to find the molar latent heat of vaporization of the two components. So we got lambda A, and now we have what? Lambda B. I hope the calculations are clear to you. You just have to get the difference between the two curves at x is equal at 1, x and y is equal to 1. That will give you lambda A, and difference at x is equal to 0, y is equal to 0 will give us lambda B. Here we have used the information that is given to us, the data that is given to us. We know the values at x is equal to 0 and y is equal to 0. We also know the values at x is equal to 1 and y is equal to 1. And we have used those values to get lambda A and lambda B. Then next task is we are supposed to locate delta D, F and delta W on this enthalpy concentration diagram. So first what I will do, I will draw vertical lines through XD. If you remember, XD that is given to us, it is 0.98. So I have drawn a vertical line through 0.98. So XD will be on the lower curve, the distillate. Distillate in this case will be saturated liquid. So XD will be obtained on the lower curve at this point. So I have located XD on the lower curve, and then I have drawn a vertical line through that particular point. Then XF is also provided, given to us. We know XF. What is the value of XF? XF is 0.45. So I am going to draw a vertical line to XF, that is 0.45. So it will be somewhere here. I will be getting this vertical line. Then XW is also provided to us. XW is 0.02. So again, I will draw a vertical line through XW. So XW will be somewhere here. And because the scale, one small division on x-axis is 0.02. So that's why XW will be located over here. And the vertical line will be drawn to that particular XW. Okay, so in the task of locating X, delta D, F and W, first we have drawn vertical lines through XD, XF and XW. Now, you must have understood it, so I'm going to erase that. So, first task is to draw those vertical lines. Delta D is located at, or the coordinates of point delta D are XD, Q1. So, XD we have drawn a vertical line through it. That means delta D will be located on this particular vertical line. And its location will depend on the value of Q1. We don't know the value of Q1. And we are going to get that from the equation for reflux ratio. What is the equation for reflux ratio? R is equal to Q1 minus Hg1 divided by Hg1 minus Hd. R is known to us. We are supposed to do the calculations for an operating reflux ratio of 2.5. Q1 we are supposed to get it. Now the question is how to use the values of Hg1 and Hd. So for that, let me tell you, Hg1 is enthalpy at this point. Let me use another color so that you can understand. So Hg1, yes to me. So Hg1 will be obtained as the enthalpy at this point. Which is this point? The point where the vertical line, intersects the upper curve. And y coordinate of that point, that is enthalpy at that point, is nothing but Hg1. What I am saying? Hg1 is enthalpy at this point. What is this point? This is the point where vertical line through xd intersects the upper curve. Once you understand this, it is easy to understand how to get Hd. Hd is enthalpy at a point where the vertical line through xd intersects the lower curve. So that is, it is at this point. So both the points, that is point for getting Hg1 and then point for getting Hd, they are located on this vertical line through xd. You please remember. And if you can read it, I will directly tell you what are these values. Hg1, that means at value of enthalpy at this point, at per this graph, you can read it. It is 12800 kilocalories per kilomole. And Hd, which you are going to read over here, it is 5100 kilocalories per kilomole. So now R is 2.5, which is given to us. Now you can easily use this equation. So 2.5 is equal to Q1 minus 1200 Hg1 divided by 12800 divided by 12800 minus 5100. Hd is 5100. So that gives us 2.5 is equal to Q1 minus 12800 divided by 7700. Because 12800 minus 5100 is 7700. So we continue with that. So we just got 2.5 is equal to Q1 minus 12800 divided by 7700. That is 2.5 into 7700 is equal to Q1 minus 12800. That is 19250, because 2.5 into 7700 is 19250. That is equal to Q1 minus 12800. That is Q1 will be equal to 19250 plus, when you take this on the other side, it will be 19250 plus 12800. Therefore, Q1 will be equal to 32050 kilocalories per kilomole. So in this way, you can get the value of Q1. And once Q1 is known to you, you can locate over here. So 32050 comes out at this point. So when you locate Q1, you move on to the vertical line through HD, and where you get the intersection, that point will be nothing but delta D. So in this way, point delta D is located. Then F is located at XFHF, or simply the line which passes through XF. So the point on the lower curve itself will be F. And if you have to get HF, you can read that value on the y-axis. We just come to this point and go to the y-axis and you get HF. But it is not required for plotting F. Once you know where the line, the vertical line passes through XF, you can locate F at that particular point. Then how to locate delta W? For locating delta W, how it is done is delta W is located on the line through XW, at which line delta D up intersects when extended. So you have one line, a vertical line that we had drawn initially through XW. Now we are going to draw a line starting from delta T, then passing through F, and then we are going to extend it so that it intersects this line, and the point of intersection is nothing but delta W. So I will draw the line. So I have drawn line delta D F, and then I have extended it so that it intersects this vertical line. So this point is nothing but the point delta W. So in this way, you can locate or you have to locate delta D, those 3 points, delta D, F and delta W. Locating this point, it's important because that is the that will be the fundamental requirement for finding out the number of equilibrium stages. Okay, now next we will find the number of stages, number of equilibrium stages, or you can say number of ideal stages, or number of theoretical stages. So for that, we will also need the distribution diagram. The distribution diagram, as you know, this is a plot of x versus y, where small x is plotted on the x-axis and small y is plotted on the y-axis. Small x, as you know, it is the mole fraction of the more volatile component in the liquid phase, and y is the mole fraction of the more volatile component in the vapor phase. So if you plot the equilibrium values, you are going to get the equilibrium curve. And this diagonal we are drawing for our reference. So this is the equilibrium curve, and for our reference we have drawn the diagonal line. So plot of x versus y, it gives the equilibrium curve. Why it is called as distribution diagram? Because every point on the curve, it gives distribution of the component between vapor and liquid phase. Vapor and liquid phases, when they come to equilibrium with each other. That's why this diagram is also called the distribution diagram. Okay, so let us start. We are going to start at this point. The process of finding the number of stages, it will start at this point. So I have marked this point and I am going to read the y value, that is y value at this point. So after locating the point, I will be coming down to the x-axis and I will read the value. So in this case, this point is lying on the vertical line through xd. Therefore, here y is equal to xt. So if you read it, you'll come to know that in this case, y is 0.98, which is equal to xd. xd, as you know, it is 0.98. So you start with y is equal to xt, and then with that value, you come to the distribution diagram and locate that y. So I am locating y is equal to 0.98. Since y is equal to xt at the start, so I am locating that point over here. Then my aim is to get the value of x that is in equilibrium with this value of y. So for that, I will go to the equilibrium curve and get the value of x that is in equilibrium with this y. Let us call it as y1 for your understanding. This is y1. And we are starting with y1 is equal to xt. Then for that y1, we'll have found out the corresponding or the equilibrium value of x. We have found out the value of x that is in equilibrium with y-rem. So for that, I will start at y-rem and then go to the equilibrium curve and then come back to the x-axis and read the value of x. So that would be x1. So in this case, you can check x1 comes out to be 0.96. So I will read this value. So x1, it comes out to be 0.96. Now what I am going to do, I will locate this x1 on the enthalpy concentration diagram. So you can see I am locating over here. So x1 is located. This x1 is located over here. So once I locate x1, I will be performing two tasks. One is I will connect this point with delta D with a construction line. So here blue color line that I have drawn from x1. So this is x1. Let me write for your understanding. This is x1 and this is y1. And for this y1, after locating y1, we have got x1. Okay. So as I said, I'll be performing two tasks. One is I'll be connecting x1 with delta D, and then I will connect x1 y1 with a tie line. Why with a tie line? Because x1 and y1, they are in equilibrium with each other. So that's why I will connect them with a tie line. So this green dashed line whose endpoints are x1 and y1, that is a tie line. The endpoints x1 and y1, they are in equilibrium with each other. So that ends the first, you can say, step. Then next, what I have to do, I have to look at this point. Now, which is this point? The point where the construction line from x1 intersects the upper curve over here. So I am locating that, and let me call it as y2. So y2 is that point where the construction line from x1 intersects the upper curve. So I am going to take this y2 and go to the distribution diagram. So I am locating y2 over here. So y2 over here I am locating, and then my aim is to get the value of x that is in equilibrium with y2. So for that, I will be going to the equilibrium curve and then coming back to the x-axis to read the value of x2. To read the value of x2. So it is 0.91 something. So now I will be locating this x2 on the lower curve of the enthalpy concentration diagram. So x2 will be located over here. x2 is 0.91. So here why it is 0.91? Because 0.9 is in equilibrium with y2. y2 in this case is 0.96. So after that, again two tasks. First task is we are going to draw a construction line from x2 to delta D. So I will do that. And then we are going to connect x2 and y2 with a tie line. So that ends second step. Then the third step is I'll be reading this value. Now I'm calling it as y3. So this is y3. And then I will come back to the distribution diagram, locate y3 on it and get the corresponding or the value of x that is in equilibrium with y3. So I get x3 over here. Now I'm going to read this value of x3 which in this case is 0.84. You can check. And then I'm going to next, I'll have to locate this X3 on the enthalpy concentration diagram. So I'll do that. So I am locating X3 at 0.84. So let me use red color. So this is X3. So again, I will first connect X3 to the point delta D by a construction line. And after that, I will be connecting X3 with Y3 by a tie line. That ends step number 3. Then after that, I will have to read the value of Y, where construction line from X3, it intersects the upper curve. So I am talking about this point. So let me call this as Y4. So this is Y4. Now you can tell me, I'm sure about that. So I'll read Y4. So Y4 in this case is, you can check it is 0.88. 0.88. So I'll come back to the distribution diagram. I will locate Y4 over here and I'll get the X value that is in equilibrium with Y4, and I'm calling it as X4. I will read this value of X4, which in this case is 0.6. How much is that? That's 0.74. X4 is 0.74, this point. So I locate 0.74 on the enthalpy concentration diagram. So over here it is located. This is X4. First I will connect X4 with the point delta D by a construction line. And in that process I am going to get, or before that, I will have to connect X4 and Y4. Because they are connected by a tie line, they will be connected by a tie line because they are equilibrium concentrations, as you can see from over here. Then after that, let us read Y5, which is over here. So Y5 in this case is, as you can say, it is 0.81. So let me write. So this is Y5. Now I will use that Y5, come back to the distribution diagram, and then I will locate Y5 over here. So this is Y5. Next I will go to the equilibrium curve and get the corresponding value of X5. X5 in this case comes out to be 0.61. So now I will have to locate X5 on the enthalpy concentration diagram on the lower curve. So X5 will be located at 0.61. So this is X5. This is X5. Then X5 will be connected to the difference point, and X5 and Y5, they will be connected by a tie line. They will be connected by a tie line. So in that process, you get this point. You get this point. Let me call this as Y6. So it is 0.72 Y6. We are using. So this is Y6, which is 0.72. So let us come to the distribution diagram. So this is Y6. Now move to the equilibrium curve and get X6. So X6 in this case is 0.48. You can read. Now come back to the enthalpy concentration diagram. Locate X6 over here, 0.48. Then draw the construction line from X6 to delta D. and then connect X6Y and Y6 with the tie line. So this is how you are going to get the tie line. So in the process, we get this point. So we are going to read the value of Y, and I'm going to call it as Y7, and it is 0.63. You can check. So this is 0.63. So I'll call this point as Y7. Just a minute. I will call this as Y7. So with this Y7, which is 0.63, I will come back to the distribution diagram and look at Y3 or Y7 over here. And now let us get corresponding X7 that is in equilibrium with Y7. This comes out to be 0.36. So this is X7, 0.36. Let us take this value of X7 and come back to the enthalpy concentration diagram. So I'm going to locate it at 0.36. So it will be located over here, and this is X7. Okay, now when you get X7, you can see we have crossed the line that is drawn through these 3 points, delta W, F and delta D. So we have crossed that point, or we have crossed the point F. So this time, the construction line will be drawn from X7 to delta W, and it will be extended so as to intersect the upper curve. So the construction line will be drawn like this. So now, instead of going to the point delta D, we have gone to the point delta W. What is the reason? The reason is we have crossed the point F. So we have drawn the construction line from X7 to delta W, and then we have extended the same line so that we get its intersection on the upper curve. So that will be Y8, the next value of Y. Before that, X7 and Y7, they will be connected by a tie line. So you must have observed we are drawing tie lines, because ultimately the number of tie lines that we draw in this process, that will be the number of equilibrium stages. Okay, so we draw the tie line X7, Y7. Now next, we will read this value of Y, which is Y8, and in this case the value comes out to be you can say 0.5. Actually it is 0.49. You can check. So let me call this as Y8. Now I will take that value of Y8 and come to the distribution diagram and locate Y8. So Y8 is now located over here. Then I will go to the equilibrium curve and get the value of X that is in equilibrium with Y8. I am calling it as X8, and the value is 0.23 or 0.24. So this X8, with this X8, I will come back to the enthalpy concentration diagram and locate X8. X8 is 0.24. So it is located over here. So the next task is we will draw a construction line. The construction line will be drawn from X8 to delta W, and it will be extended so that it intersects the upper curve. So this is the construction line. And after that, X8 and Y8, they will be connected by a tie line, because X8 and Y8, they are in equilibrium with each other. Then we have to read the next value. For how long are we supposed to do this? Till we cross this line, the vertical line through XW or delta W, you can say. So now let us read this Y value of y. This will be y9. This will be y9. And what is that value? It is 0.34. So let us come back to the distribution diagram. So 0.3, not 34, it is 0.32. So we are locating y9, 0.32, then going to the equilibrium curve and then reading the value of x9, which in this case is 0.12. 0.12. So let us come with this value of x9. Locate that over here. Let me write it. So I am locating over here x9 and then we will be drawing the construction line through x9, and then x9 and y9, they will be connected with a tie line. So in that process we get this point. So that will be y10. And what is that value? The value is 0.16. 0.16. So this is y10. Y10. Then I'll come back with this value 0.16. So this is my y10. Let me write over here so that there is no confusion. And then I'll go to the equilibrium curve and get the corresponding value of x10. This is x10, and x10 you can see it comes out to be 0.05. 0.05. So with this value of x10, I come back to the enthalpy concentration diagram and locate x10 over here. And then I'll draw a construction line through x10, and x10 and y10, they will be connected by a tie line. They will be connected by a tie line. In that process, we get this point. We are going to read it as y11 or y11, sorry. So just a minute. Let me change the color. So this is y11. And what is that value? You can check. It is 0.02, 0.04, 0.06. So I'll come back with this value to the distribution diagram. I will locate y11 and then get the corresponding value of x11. So over here I get x11. It is almost 0.02. It is almost 0.02, x11. So I will locate that x11 over here. So that will be x11, which is equal to 0.02. Then x11, through x11 I will draw the construction line. Actually over here it is overlapping over the line, that is the red line. And then x11 will be connected with y11. So in that process you get y12, which in this case is y12 is equal to 0.02, because the construction line and the line, the red line to XW, they are coinciding. So I will locate y12 over here. So y12 is located now over here, and then corresponding x12 will be 0.01. So I will locate 0.01, and then I'll draw the construction line and connect x11 with y12. So at this point of time, we have reached the line, the vertical line that is passing through XW. So we have to stop. Now the task left is we have to count the number of tie lines that you have drawn in the process. So this is 1. Let me show you. So this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, this is 9, this is 10, this is 11, and the last one is number 12, which connects X12 with Y12. So that means in this case, the number of ideal stages are 11. We have counted 12 tie lines. So in those 12 stages, 12 tie lines means 12 stages. So in those 12 stages, there are 11 stages in the column and there is one reboiler. So in this way, you can use the Ponchon-Savarit method to find the number of stages in the number of equilibrium stages in a typical tray column. And number of stages in the rectifying section. That means tie lines before the line to delta W, F and delta D. So there are 6 stages, 1, 2, 3, 4, 5 and 6 before this line. And number of stages in the stripping section, the remaining stages, 1, 2, 3, 4 and 4 stages, and one is the reboiler. And feed is the 7th plate. Feed plate is the 7th plate because 7th tie line, it crosses or it intersects with the line through delta W, F and delta D. So in this way, there are 11 stages. 6 stages are in the rectifying section, 4 stages are in the stripping section, 7th is the feed stage and feed plate, and there is one reboiler. So in this way, you have to find number of stages in the case of or by the Ponchon-Savarit method. I hope you have understood the steps that are to be followed. If you have any doubts, you please mention that in the comment section. Next is, let us learn how to find minimum reflux ratio. So for that, again, we will need the enthalpy concentration diagram with the stages and then the distribution diagram. Now the task is, we know we are interested in the case of minimum reflux ratio, we are interested in a tie line that passes through F. So why this tie line is important? For that, you have to refer my video on on steps involved in the Ponchon-Savarit method. I have given link to that video in the description section. So simple is, we need to draw a tie line, or we need to find concentration in the vapor phase that is in equilibrium with XF. So XF, as you know, it is 0.45. So I'll simply locate that and try, because my objective is to get the value of Y that is in equilibrium with XF. So XF is 0.45. So I'm locating over here. I'm going back to the equilibrium curve and then I'm reading the Y value that is in equilibrium with XF. So in this case, it is 0.7. So I'll take this value of 0.7 and locate it on the upper curve. So 0.7 is located over here. 0.7 is located over here. And after locating that, I'm drawing a line through F. So why? Because in the case of minimum reflux ratio, the construction line and tie line, they coincide with each other. So first, we have located XF. We have found the corresponding vapor phase composition that is in equilibrium with it. It is 0.7. So I have located 0.7 over here. And then after locating this point, I have drawn a line that passes through this point and F. And then I have extended it so as to meet the vertical line through XD and the vertical line through XW. So this point will be delta DM, that is difference point for minimum reflux ratio, and this point will be delta WM, that is a difference point for the case of minimum reflux ratio, then Q1 dash, it will be the y coordinate will be was Q1 dash, and value of Q1 dash, if you read, it comes out to be 23,000 kilocalorie per kilomole. 23,000 kilocalorie per kilomole. What is that value? The value that we read for this particular point, 23,000 kilocalorie per kilomole. So we are going to use this value of Q1 dash for finding the reflux ratio, minimum reflux ratio. So let us get that. For that, the reflux ratio, we know it is given by this formula. R is equal to Q1 minus Hg1 divided by Hg1 minus Hd. And if Q1 is replaced with Q1 dash, the value that we just read, that will give us the minimum reflux ratio. So Q1 dash is 23,000 kilocalories per kilomole. We have just found out. Hg1, previously we got it 12,800 kilocalories per kilomole. And Hd is 5,100 kilocalorie per kilomole. So if you use all these values, R minimum will be equal to 23,000 minus 12,800 divided by 12,800 minus 5,100. So that gives us R minimum as 1.82. So in this way, you have to find the minimum reflux ratio. For finding the minimum reflux ratio, location of Q, delta D m and delta W m is required. How they are located? They are located by drawing a tie line that passes through XF and YF. How to get YF? YF is the concentration in the vapor phase, mole fraction of the more volatile component in the vapor phase, that is in equilibrium with XF. So then locate XF, you already have that point F, and then you just have to locate YF, then draw a line through FYF, extend it to the vertical line through XD, and where the intersection occurs, you get delta dm, and then read the y coordinate of that point, that will be Q1 dash, and then use this formula to get R minimum. So in this way, minimum reflux ratio has to be found. Now let us find minimum number of stages. So for that, again, we will need the two plots, that is the enthalpy concentration diagram and then the distribution diagram. The procedure is same. Now you know what steps we followed for finding number of stages. But the difference in this case is the construction line, here they will be vertical. In the case of finding number of stages, we were connecting construction lines with the point delta D. Here we are not going to do that, because when the column is operating under total reflux, delta D will be located at an infinite distance. Delta W will also be located at an infinite distance. So the meaning of this is the construction lines will be vertical when the column is operating under total reflux. Why they are vertical? Again, you please refer my discussion on steps in the Ponchon-Savarit method. I have given link to that video in the description section. So again, we will start with Y1. We are going to read that over here. I am calling it as Y1. So this is Y1. And we will come back to the distribution diagram, locate Y1 over here. Then our aim is to get X1, which is in equilibrium with Y1. For that, you will have to go to the equilibrium curve, come back to the x-axis, and that will be X1. In this case, it is 0.96. So locate X1 over here, 0.96. So this is X1. Now, as I said, while drawing the construction line, this time the construction line will be vertical, a vertical line through X1. So after drawing, because this line is going to meet delta D which in this case is at an infinite distance when the column is operating under total reflux. So you get x1, y1, connect x1, y1 with the tie line as usual. So in the process, you get y2 over here. So let me just show this is y2, which in this case is equal to 0.96. So again, we will locate y2 over here and get the corresponding x2 that is in equilibrium with y2. So just a minute. So this will be x2. So in this case, it is, you can say it is 0.9 x2. So come back to the enthalpy concentration diagram, locate x2, draw vertical construction line through it, and then connect x2, y2. So you will get y3. So y3 will be equal to 0.9. That is, in this case, it is equal to x2. Yeah, you can check. So this is then next you have to locate, you have to come to the distribution diagram, locate y3, x2 and y2, they will be connected with the tie line. Then go to the equilibrium curve, get x3, come back to the enthalpy concentration diagram, locate x3, draw a vertical tie line, vertical construction line through it, connect x3 and y3. You will get this point, that is y4, which in this case is 0.78. So come back to the distribution diagram, locate y4, go to the equilibrium curve, get the corresponding value of x4, which in this case is 0.56. Come back to the distribution diagram, enthalpy concentration diagram, locate x4, which is 0.56, then draw a vertical line through x4, then connect x4 and y4 with a tie line, read this as y5. So in this case, y5 is equal to x4, that is 0.56. So locate 0.56. Before that, x4 and y4, they will be connected with a tie line. Then locate y5, get the corresponding equilibrium value of x, let us call it as x5, which in this case is 0.29. Come back to the enthalpy concentration diagram, locate x5, draw a vertical line through x5, connect y5 and x5 with a tie line. In the process, you get y6, which is equal to x5, that is 0.929. Come back to the enthalpy distribution diagram, locate y6. So this is y6, get the corresponding value of x6, which is 0.11. Come back to the enthalpy concentration diagram, locate x6, draw a vertical line through x6, connect x6, y6 with a tie line, get y7, which in this case is equal to x6 and which is 0.11. Then come back to the distribution diagram, locate y7 and get the corresponding x7, which is 0.04. So come back to the enthalpy concentration diagram, locate x7, draw a vertical line through x7, connect x7, y7, and then read y8, which is equal to x7 because you have drawn a vertical line. So that is 0.04. So this is y8 and get the corresponding x set. X set comes out to be 0.01. So locate that, draw a vertical line and then connect. This is x set and then you are connecting exit and Y8 with a tie line. So in this process, you crossed the vertical line through XW. That means you have to stop. And now just count the number of stages. So this will be minimum number. So this is stage 1, stage 2, stage 3, stage 4, stage 5, stage 6, stage 7, and stage 8. So that means in this case, the minimum number of stages are 8, out of which 1 is reboiler and remaining 7 are the stages in the column. So in this way, the only thing that you have to remember is those construction lines are to be drawn vertical. And you have to follow the same process or same procedure which we followed for finding number of ideal stages. So I hope now this is clear to you how to get the minimum number of stages, which happens to be the case when the column is operating under total reflux. Next is we have to get condenser and reboiler heat duties. So for that we will need this because we are going to read Q1 because we are going to use that in the calculation, and we will also use Q2. So in this case, for condenser heat duty, we are going to use equation for Q1. And the equation for Q1, we have discussed it previously. It is QC plus DHT upon D. Our aim is to get QC. So for that we need Q1 and we are going to read it over here. So if you read Q1, it is 32050 kilocalorie per kilomole. 32,050 kilocalorie per kilomole. Then D we calculated previously, it is 21.68 kilomole per hour. HD we had used this value earlier, it is 5100 kilocalorie per kilomole. So if you use all the values, 32050 is equal to QC plus 21.68 into 5100 divided by 21.68. That is 32050 into 21.68. I have brought this to this side. So is equal to QC plus 110. This multiplication is 110568. That is, this multiplication is then 684844. That is equal to QC plus 110568. That is QC is equal to 684844 minus 110568. That is QC is equal to 584276 kilocalories per hour. So this is the rate at which heat is removed in the condenser. So the important thing over here is we need to know the value of Q1 and all other values. Condenser heat duty is QC. Now let us find out the reboiler heat duty. So for reboiler heat duty, we are going to use equation for Q2. Q2 is WHW minus QR upon W. So Q2 you'll be reading over here. So it will be a negative quantity. So in this diagram, Q2 is minus 16,000 kilocalorie per kilomole. W was calculated earlier. It is 26.72 kilomole per hour. Then HW is 5800 kilocalories per kilomole. Again, HW you have to read at a point. It will be the y coordinate of the point at XW. So in this case, XW is here, through which the red vertical line is passing, and we are reading y coordinate, that is 5800 kilocalories per kilomole. So if you use those values, it will be minus 16,000, that is equal to 26.78 into 5800 minus QR divided by 26.72. That is minus 16,000 into 26.72. That is equal to 154976 minus QR. Because this multiplication is 154976. And this multiplication is then minus 427520. That is equal to 154976 point QR. Minus QR, sorry. and then QR is equal to 154976. When this will come on this side, it will be plus 427520, and which gives us QR as 582496 kilocalories per hour. And you can check for yourself. QC is almost equal to QR. You can check. So that means that suggests that whatever amount of heat is provided in the reboiler, same amount of heat is removed in the condenser. You can check the value for QC. It is almost equal to this value. So heat losses from the column, they are negligible in that case. So with this, I end my discussion on how to solve numerical, how to get number of stages by using Ponchon-Savarit method. So we have learned how to find out the equilibrium stages, how to get the minimum reflux ratio, how to get minimum number of stages, how to calculate condenser and reboiler heat duties. So lot many things we have learned in this particular discussion, and I am sure that you'll not find any solution as simple as the one I have discussed in this particular video. You please watch it carefully. You know every fundamental aspects of the Ponchon-Savarit method. And again, if you have any doubts, you please mention them in the comment section. You can also mention what the topic that you have you would like to learn. I will make video on that topic. For now, thank you for being with me. I will end my discussion. I hope you have gained something after watching this video. So that's why thanks for watching my video. Do subscribe to my channel. Tell your friends to subscribe to it. If you have any doubts, you please mention them in the comment section. If you want any topic to be covered in my discussion, you please mention that in the comment section. For now, have a nice day. Bye bye.